Okie dokie, friends. So in this screencast, we get to take a look at a very mathy word. We get to take a look at extrema, which is the plural of extremum, which just means maxes and mins of a function on some interval. This screencast gets very, very heavy and very, very heady early on. And in fact, most of the way through, we're in definition land. But by the end, we'll take a look at some of the practical outworkings on what it means to find an extremum on an interval. So, if I may, a couple of pictures. Oh, we'll go blue. On the red function, would you agree that this red function has a max? Sure it does. That right there is the max value. And the function hits that max value one time at that point right there. Would you agree that the red function has a minimum value on this interval? Sure. And that minimum value is this value, and it's here and it's there, but the function hits the minimum twice. Over on the blue function, would you agree that this function has a minimum value? Sure, that's your minimum value. And that minimum value is achieved twice. Doesn't have to be twice, it just happens to be twice. Does this function have a maximum value on the interval? Well, I'm less convinced. I don't think that's a maximum value because there's a hole in the function. So if we were to say that the max value was right there, well, the function doesn't hit right there. Let's pretend that this is at 2. And you say, well, no, really the max value is 1.99999. Well, we get closer than that. Well, then it's 1.9999999. Well, no, we get closer than that. And as soon as you start saying, well, it's 1.9 repeating, well, then that's 2. So there is no absolute max over there. Let me formalize some things for you. Let f be a function with a domain of D. Then f of c is the, and I'll define two things. F of c is the absolute max value on the domain if and only if f of x is less than or equal to f of c for all x in D, and f of c is the absolute minimum value on D if and only if f of x is greater than or equal to f of c for all x in the domain. So what do I mean? 0 is the absolute minimum value on D because the function is always at least as big as 0 on the domain. Yes, 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 yes. The function is always at least as big as 0. Similarly over here, the function is always at least as big as 0. Over here, I've got a maximum value here. This is the absolute max on the interval because the function is always no bigger than f of c. No bigger than, no bigger than, no bigger than, no bigger than, no bigger than. But over on the blue side, there is no absolute max because whatever I think the absolute max might be, I can get closer to it. There are values of x for which the function is bigger than whatever I think the maximum value is. And that's what's going on there. In fact, we have a theorem that we should talk about. If f is continuous on a closed interval AB, then f has a max value and a min value on AB. As soon as you have a continuous function on a closed interval, that function must have a maximum value and a minimum value. So I'll just draw for a little while. There. This function is a continuous function on a closed interval from a to b. This function has a maximum value and a minimum value on that interval. The absolute maximum value is f of that guy, and the absolute minimum value looks like it's f of that guy. A little bit of vocabulary. This thing is what we call the absolute max. This thing is what we call the absolute min, which leads us to ask the question, well, what about that? What about that point? It's a max, but it's not the max. And so we would call this a relative max or a local max. And similarly, we would call this a relative min or a local min, and that just depends on your textbook, whether it's called relative or local. By definition, f of c is a local max value at c if f of x is no bigger than f of c for all x in some open interval containing c. And similarly for local mins. That is to say, I can draw an open interval around that min for which that is the lowest point. Therefore, I have a local min. Side note here. Side note. If f of c is an absolute extremum, an absolute max or an absolute min, then f of c is also a local extremum. So all of the absolute extrema are local extrema, but not all of the local extrema are absolute extrema. I told you we'd be heady. So here's the question, taking a look back at this picture. How do we find extreme values? I mean, what do we notice? Talk calci to me. What do we notice about derivatives at that point, derivatives at that point, derivatives at that point, the derivative at that point? What do we notice? Well, it looks like flat tan, flat tan, flat tan, flat tan. And so, sure enough, we have a theorem. And the theorem goes something like this. If f has a local max or min value at an interior point, we'll call that C of its domain, and if f prime of C exists, then f prime of C is 0. And sure enough, I have a max, the derivative exists, the derivative is 0. I have a min, the derivative exists, the derivative is 0. Okay? That makes sense. I'm going to talk about the logic here. The logic here says if this is true and if this is true, then that is true. It does not go the other way, and both of these have to be satisfied for this to come true, because we could take a look at this, which very clearly has a max, but very clearly does not have a derivative value at that point. That's the cusp. Similarly, we could take a look at this function, which very clearly has a min, but no derivative value at that min. Furthermore, we could take a look at this function, like x cubed, which clearly has a place where the derivative is 0, but no max or min at that point. So if there is a local max or a min, and if the derivative exists, then the derivative is 0, but not necessarily. And just because the derivative is 0 doesn't mean you have a max or a min. All right, almost there. One more definition and then some practicality. A point in the interior of the domain of a function called f, at which f prime equals 0 or f prime does not exist, is a critical point. It is a critical point. And here's the upshot, friends. Extrema occur at endpoints of the interval or critical points within it. If I'm going to find extrema, they are either going to happen at an end point or at a critical point. They're either going to happen at an endpoint of the interval, there's a local max, there's a local min, or I'm going to look at a critical point, someplace where the derivative is 0, someplace where the derivative is 0, someplace where the derivative is 0, someplace where the derivative is 0. So time to get purely practical with you. Find all extrema of f of x equals 2x squared minus 8x plus 9 on 0 to 3. So I'm going to consider the endpoints and then the critical points. I want to know what f of 0 is, I want to know what f of 3 is, and I want to know what the function is anywhere that this function turns around. So the endpoints are easy. F of 0, that's easy. F of 3, that's a little arithmetic, but that's not even too bad, just subbing into the function. Critical points, that's a different matter. To find critical points, I want to know when f prime is 0. So I want to know when 4x minus 8 is 0, and so x is 2. So I want to find f of 2 because that's the other possible place where I could find an extremum. And it turns out that f of 2, a little bit of arithmetic, is 1. So always answer the question. To find extrema requires us to find an absolute max and an absolute min. The absolute max is the one of these that is bigger than the others. That's 9. And it occurs at x equals 0. The absolute min is the one of these that is smaller than the others, and that's 1, and it occurs at x equals 2. So from a purely crank it out standpoint, if I ask you for extrema, you find the function value at the endpoints, the function value at any critical point within the interval. One of those is bigger than the others, that's your max. One of those is smaller than the others, that's your min. So for you, we can find extrema. We can find extrema for g of x, which is 1 over x squared plus 1 on 0 to 2. And we can find extrema for h of x is x cubed minus 3x squared plus 3x minus 2 on the interval from 0 to 3. Take a moment, find the function values at the endpoints, at any critical points, and see which ones are bigger than the others or smaller than the others. Okay, here the max value is 1. It occurs at x equals 0. Here the min value is 1/5. It occurs at x equals 2. Over here the max value is 7. It occurs at x equals 3. And the min value is -2. And it occurs at x equals 0. So hopefully you can get a sense of what kinds of things we'd like you to be able to do with Extrema on an interval. Awesome. We'll go to class. We'll talk about it. It'll be good.